Okay, so here we're gonna introduce a theorem to tell me right away whether a graph has an Euler trail or an Euler circuit, right? And again, an Euler circuit is an Euler trail, right? It satisfies all the conditions, right? The Euler circuit just adds an additional thing to accomplish is that you end up at the same one. All right, so the intuition here before I introduce the theorems here is we want to think of, right, we saw in the previous video that the odd and evenness of the vertex is probably going to play a role in here, right? So the reason for that, so let's think of an odd degree vertex here, right? Just without kind of loss of generality, we'll just keep it at 3, right? One, we could see it's easy why that won't work, right? If it was 1, let's look at a basic graph here. All right, one way to guarantee there won't be a circuit, an Euler circuit, is if you just kind of spike it out there, right? Because at that point, right, once you, even if you start there, there's no way to get back. But even if you don't start there, once you go there, there's no way to leave, right, without traversing a an edge that you've already crossed, all right? So here, let's take a look here. And again, here, there's other stuff going on in this graph, right? So things are going on here, right? Here, I don't know. The idea is I have a vertex of odd degree, all right? Now, if you don't start here, you will eventually get stuck if this is an odd degree, right? So let's say you don't start there, right? So if you don't start there, what must happen here, right? If you don't start there, that means that, all right, you wind up at that vertex, then you leave, right? And you're able to, again, if we want an Euler trail, an Euler circuit, right, and every edge needs to be crossed, right? So eventually when you come through this edge here, that is it, right? You'll be stuck there. Now that may or may not be your last starting point there, your last edge that you've traversed. So maybe it's okay that you get stuck there. But now keep in mind there, that means that if you didn't start there, there's no way that you can be a Euler circuit, right? Because you will get stuck there and you didn't start there. Okay? All right. Now, if you start there, right, so let's say you did start there. All right, that means here, if you started here, you went out, you left, right? Then you came back right after, you're traversing all your edges here, right? So you left, you came back, and now you left again. So you can no longer return there. So you can't end up there either. Okay? All right. So that means that, right, a condition that is going to be required here for an Euler circuit is that, excuse me, is that the vertices must all be of even degree, because you need a way to start or leave, come back, right? And if you leave and come back, it has to be done in pairs, right? So if you start there, you need one to make sure that you can get back, okay? So that they come in pairs, right? And if you didn't start there, right, then you need a way to reach that vertex through an edge, but also leave it, okay? So for an Euler circuit, right, it's okay, or excuse me, it's gonna be necessary to have even degree vertices for an Euler circuit. Now, for a trail, right, as we can see here, a trail does exist here, right? You can, if you start here, you can go here, 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 right? So as it turns out, that's okay, right? But I can't have it more. I can't have more than 2 essentially odd vertices, right? Because if we're leaving and coming back, I need a way to only one of those, right, or at most two, right, can be odd, right? And if I do have an odd circuit, then an odd degree, then I want to start there, right? And then I will end at the other one, okay? So, and that's just because of the nature, once you arrive at a vertex, you need an edge to get out of there, unless that's going to be your last one, right? So if it's odd degree here, then you can traverse it, right? If you start there, you can start, you can get back, but then once you leave, that's it. It's no longer, you can no longer be there. You can no longer return there. All right, so now let's take a look at the theorem. All right, so here's what I'm going to state the theorem. So the theorem will be stated with, I won't go through the proof here. All right, so here on Euler circuit, so we say here a connected graph has an Euler circuit if and only if, so here I have an equivalent statement, if and only if every vertex has even degree. Okay, all right. And an Euler trail, right, a connected trail, so excuse me, a connected graph has an Euler trail if and only if there are exactly zero or two vertices of odd degree. Okay. All right. So now returning to our bridges of Königsberg problem, we could see for this particular problem, every single vertex has odd degree. So now we know that there is no way to traverse, there is no Euler trail or Euler path that exists. All right, so if you want to visit all the bridges, you will need to cross bridges more than once. Okay. All right, let's take a look. Here's some okay, so here let's look at some graphs here. All right, so these are from our textbook here. All right, and so let's take a look at the graphs here and determine, do I have an Euler trail or circuit? Now looking at the graph G1, we'll start here. So I see we have 4 vertices that are odd degree, right? Those top 4, right up there, right? They're all odd degree, so no trail or circuit exists. Right, so G1, neither. Now G2, so here we have 3 vertex of degree 3. This is degree 3. This one here is 1, 2, 3, 4. Okay, that's fine. 1, 2, Okay, so this one is 1, 2, 3, 4, 5. That has 2. And this one is 1, 2, 3, 4. Okay, so it looks like we have 2 odd degrees. So no circuit, but it looks like we do have a trail. Okay, now in order to find that trail, it is important that you start at the odd one and you will end at the other odd vertex. All right, so G3, right, example I did previously in a previous video. So all these have even degree, right? So it has both a trail and a circuit. Now, one thing to realize here that in picking a starting point, right, if it has a circuit, it doesn't matter. They're all even. So you can generate a circuit from whichever vertex you want here. All right, so now let's take a look at G4. All right, so G4, you can see here, so 2, degree 2, here this one is 1, 2, 3, 4. Same 4, this one is 4, 1, 2, 3, 1, 2. So those bottom have degree 3. There's 2 of them, so there's no circuit, but there will be a trail, and you want to start at the bottom, one of the bottom ones, left or right, and you'll end up at the other odd degree vertex. Okay, now looking at G5, we can see, okay, so this is degree 2, 2, 3, 4, 1, 2, 3, 4, 2, 1, 2, 4, 4, 4, all even. So G5 has a circuit and a trail, right? Okay, and then G6, we can see all these outer ones are odd degree, so there's 4 of them. So we will have neither a circuit nor a trail. Okay, all right. Okay. All right, so in the next video, we'll talk about something called a Hamilton path, right? So a different but a related type of problem.